Okay, welcome to the March Estes Park Group. This month we have Dr. Dave Raggett presenting. He's a web pioneer, lifelong interest in AI, gained experience at the University of Oxford in the Machine Intelligence Research Unit at the University of Edinburgh, the Logic Programming Department at Imperial College, the Computer Science and AI Lab at MIT, and many years at HP's lab, Knowledge-Based Programming Department. He's now a member of the W3C, ERCIM, and involved in a succession of European projects. He founded W3C's Cognitive AI Community Group and is driving ongoing work on human-like AI. Holds an honorary professorship from the University of West England and is going to speak to us today on the role of symbolic knowledge at the dawn of AGI. So with that, Dave, I will hand it off to you.
Okay, well, thank you, and thanks everybody for your time. And I'll go through, quite a lot of things, but the slides I believe you've already been sent the link to the slides, so you can have a look at those. And they're happy to follow up with email afterwards. So I'm going to talk a bit about, first of all, the required slide about W3C and ESIM, then talk about evolution in ICT systems, the limitations of logic, and why we need to move to argumentation. The work that I've done in that area on implementing a format for that and with web-based demos, and the need for strategies and tactics for generating coherent and effective arguments. Then limitations of symbolic AI, and similarly the limitations of generative AI, despite all the hype at the moment. And then my cut at artificial general intelligence and the work that I've started on kind of future neural networks, along with the need for semantic interoperability, and then I'm going to wrap up with some discussion topics, and hopefully there will be a bit of time for discussion. So W3C is an internationally member-founded community, and I've been involved since the very beginning. I got involved in the web back in 1992, so you can blame me for HTML tables and some of the work problems we had with forms and things like that, and also launched the HTTP working group, the ITF. So anyway, W3C is going strong, and we have many different groups, working groups, community groups. So as you heard, that I've set up a community group on cognitive AI, which is open for anybody. You don't need to be a W3C member to join that. So I think when it comes to ICT systems, a lot of businesses are still using relational databases, SQL and all that, which is kind of a bit awkward because it's complicated to design in the first place. And then it's adapting your database and your applications to match new requirements is very expensive. So graph databases are a little easier, and so they are growing quite rapidly at the moment. And of course, we have W3C's framework, RDF, the Resource Description Framework, and then we have other kind of things like property graphs and so forth, and a variety of standards around those. And I'm also involved in the RDF Star working group, which is kind of trying to make RDF slightly easier to express statements about statements. And then I think the future will lie with cognitive databases and human-like AI. So this will give us dramatically increasing flexibility and ease of development. So through the ability to cooperate through natural language and multimedia for cooperative problem solving. So I think that's where the future's going. It won't happen immediately, but we're making steps along that path right now. So first, I want to talk about the limitations of logic and deductive proof. So logic deals with mathematical entailments, what is held to be true. This assumes perfect unchanging knowledge. But logic isn't really applicable if knowledge is uncertain, context-sensitive, imprecise, incomplete, inconsistent, and changing, i.e. everyday imperfect knowledge. However, that is the problem that as individuals or as systems, you never know everything. Your knowledge changes as you learn. So defeasible reasoning is much broader than logic and forms the basis for legal arguments, ethics, political arguments, and everyday discussions. And we should embrace the challenge to move on from logic to arguments. So what is defeasible reasoning? It's essentially replacing deductive proof with defeasible reasoning about arguments for and against suppositions. And strict rules logically entail their conclusions, while defeasible rules create a presumption in favor of their conclusions. But, as you get new evidence coming in, you have to change your mind, which is something, that's not the case for conventional logic. So arguments are in support of or counter to some supposition, building upon the facts in the knowledge graph or the conclusions of previous arguments. And the preferences between which arguments you like are derived from the preference between the rules of additional consideration with respect to consistency. And then there's, the counter arguments you can classify into three groups. You can undermine another argument, or you can undercut an argument, or you can rebut an argument. So there's different sort of ways of doing this. And essentially, you need to use tactics to figure out how to construct those. So argumentation theory, and it's not new. The Stanford Encyclopedia of Philosophy lists 5 types of arguments: deduction, induction, abduction, analogy, and fallacies. And there's been studies around argumentation and rhetoric made by a long line of philosophers dating back to ancient Greece, like Carneades and Aristotle. And then we had more mathematically oriented logicians such as Frege, Hilbert, and Russell. And then as Stephen Toulmin criticized the presumption that arguments should be formulated in purely formally deductive terms. After all, every day in legal arguments are not. Douglas Walton extended tools from a formal logic to cover a wide range of arguments, and he's got a great set of argument schemes. And then Hahn, Oxford, and others have applied Bayesian techniques, sort of the Bayesian inference and reasoning. Then there's the work from the University of Dundee in Scotland on the AI efforts and ontologies intended to serve as the basis and interlingua between different argumentation formats. And I'm particularly keen on the work by Alan Collins in the 1980s and his colleagues. He applied a more intuitive approach to plausible reasoning that takes sub-symbolic knowledge into account to sort of model rough notions of metadata in lieu of statistics, which are often not available. So Collins inspired my work on the plausible knowledge notation, which I'll present to you shortly. And again, this is built arguments in support of or counter to some supposition. And so as we said before, so here's some example or some insights into what we mean by plausible inferences using prior knowledge. So if you have a class, you may be able to, you've got properties and relations associated with that class, then you can specialize that, some of that knowledge will apply to subclasses. And then vice versa, if you know about some subclasses, maybe you can generalize some things you know about the subclass to the parent class. And the expected certainty of such inferences are influenced by qualitative metadata. I don't have time to go into details, but they're sort of named here like typicality. I don't know, like robins are typical of songbirds. Similarity, whether two things are roughly similar. The strength of the concept and its inverse. The dominance within the population, the multiplicity scope, and so forth. Then we can have with the implication rules. So if you have a rule which says if it is raining, then it is cloudy, then you can also run this in reverse. With the appropriate metadata, you can infer that if it's cloudy, it may be rainy, and if you have, if you know roughly how often that's likely to be the case, that gives you some degree of certainty. So that's opposite from regular logic. So the idea is logic is weak because it doesn't really account for the kind of the metadata and the kind of weaker inferences that you have with imperfect knowledge. So then we have analogies and the idea of insights gained by batching structural relationships from one domain to another. And then we have scalar ranges and through the use of fuzzy logic and the work by Zade et al. For example, fuzzy terms like cold, warm, and hot, which are kind of a kind of fuzzy blend of the temperatures. Then something can be both cold and warm at the same time to different degrees. Fuzzy modifiers like somebody is very old. What does that mean? And fuzzy quantifiers like few people, like, I don't know, whatever. So you can have multiple lines of arguments for and against the premise in question, drawing upon these. So I'm going to show you that this is an example of this is a web-based demonstrator I've put together. And as you can see the URL at the top, and there's a link at the bottom left. And so basically it's a proof of concept implementation of the plausible knowledge notation with a large collection of examples that you can sort of cycle through. And the kind of the arguments are presented at the top window, and then below that you can look at the the knowledge graph that contributes to that. And so the example here is we have a premise: flowers of England includes daffodils, and it's looked at the knowledge base and come up with the various lines of arguments suggesting that. And we can see things like certainty, as in this case, is certainty high because the facts are fairly strong. And then we can look from further information, seek additional evidence, work a little bit harder, think a bit longer. The trace button checkbox allows you to see what it's doing because it works in two passes. It avoids circular arguments, and it generates the explanation in a second pass after a backward trace through the proof, or the argument. Here's some further examples. Example, the top one here: climate of Belgium includes temperate, so that's like a property. And so we have the includes, basically the sort of set relationships like includes or excludes, and guilt of accused excludes guilty. Then we can have relationships such as roses are a kind of temperate flowers, and circuits analogous to plumbing. And then relationships can also be scoped. These statements can be scoped so that they apply within some context. And so you can talk about flow increasing of pressure for plumbing and current increases of voltage for circuit. And that they are actually represent an analogy. So we have that in the next statement: flow current. Flow is to current as pressure is to voltage. And then you can have queries, and it's like dog is to puppy as cat is to whatever, like kittens. And then we have implication rules with variables like question mark place. Then we have the metadata: strength high, inverse low. So running the rule forwards, the inference is strong, whereas running in reverse, the inference, the likelihood or the certainty is low. And then we have the ability to express kind of ontological knowledge. I won't go into details here, including ranges. And then we have queries, query language, and we can have, the example, we have which X, where X is a person, the age of X is very old. That's involving a fuzzy modifier. And then we can have things like count and then a fuzzy quantifier like few. And then we can also have statements about statements like Mary believes that John says John loves Joan is a lie. Okay, so anyway, this is a railroad version of the grammar generated online. So I don't have time to go into details of this unless you have questions later. So we have context-dependent relations, like Belgium is similar to Netherlands for latitude. We have fuzzy ranges and context sensitivity. For example, the meaning of age depends on who you are. Like if my grandchildren's view of who is old is kind of rather different from mine, because I'm nearly 70, so I think of old as being people who are like 90, whereas they think of people as old as being like 20, perhaps. And then you have fuzzy modifiers, fuzzy quantifiers. And then there's this idea of imagination or abductive reasoning. So planning, what if analysis, understanding intent, modeling stories, report to speech. So this involves this idea of named and unnamed collections of statements. Then we have reasoning over related ontologies, and I use the example of climate here because there are different terminologies for climate. They're not directly equivalent. So you can't just say something is you can't do a direct relationship, but you can make arguments that given you have some information for one terminology, you can make kind of a reason about another terminology with sufficient knowledge. So these terms are associated with typical weather patterns, like in the cities like Shanghai, Buenos Aires, Sydney, and Hong Kong. And then this points to the potential for defeasible reasoning, as there's no one way to relate the terms. It's more about searching support for and against, or for and counter to the supposition. Varying degrees of certainty, you can't prove things so much. So then there's these strategies and tactics for argumentation. Further work is now needed on an intuitive syntax for reasoning strategies and tactics, as well as ways to model pathos, the role of feelings and emotions, because in human arguments, feelings and emotions are an important part, an ingredient. So this builds upon the well-established principles for arguments and rhetoric dating back to Aristotle. So ethos for establishing credibility to engender trust, saying I'm an expert because blah, blah, blah. pathos, using emotion to stir people's feelings, logic to emphasize rational support, Kairos, which is some opportune, it's timely and topical in nature, using things that people remember and easily. And then there's the use of rhetorical questions to strengthen your support, sort of quite often used in political discussions. So here the idea is to gather use cases and a suite of examples to work on that. Then I switched to topics to cognitive AI. So cognitive AI, you can sort of loosely define it in terms of these sort of set of other topics like human intelligence, thinking, problem solving, memory, learning, language, perception, actuation, attention, feelings, and emotions. And the cognitive sciences have been going for a long time now, and there's a lot of value if we can learn what we can gain inspiration from what they've learned. So it's the interdisciplinary study of the mind and its processes, with subfields like linguistics, psychology, neuroscience, philosophy, AI, and anthropology. And there have been decades of work on understanding the mind, how we learn, the kind of mistakes we make. And this can provide deep insights for working with neural networks. And there's a lot of work now on mixing symbolic and sub-symbolic models. So I'm particularly a fan of the work by John R. Anderson, and so at CMU, and he's been working on this for many decades. So ACTA is a popular cognitive science architecture, and I kind of reconstructed that with the simpler syntax I'll explain in a moment. Alan Collins, as I mentioned, on plausible reasoning, Dedra Gentner on analogical reasoning, Lotfi Zadeh on fuzzy reasoning, and Lakoff and Johnson on metaphors. So when we want to look at sort of AI and language processing, it's useful to look at how humans process language. And the evidence from a variety of sources like isoCades, when you're reading text and looking at what you're looking at, which words you're looking at, the buffering limitations, like a few words, not thousands of words, semantic priming effects, and of course, brain scans. So all these things lead to the idea that human language processing is sequential, hierarchical, and predictive, and combining as kind of a bottom-up processing for sounds and syllables, and top-down using the context and prior knowledge. So it also involves incremental learning vocabulary. And anyway, there's a link to some papers. Then there's this architecture on my cognitive architecture for artificial minds, which is aimed at both symbolic and neural network implementations. And so essentially we have a kind of a blackboard, the cortex, which is like multiple specialized graph databases and algorithms, which can execute in parallel. Then there are a number of systems which connect to it with circuits, such as perception, system 1, system 2, and actuation or actions, which is a kind of real-time parallel control. So I won't go through the details of this, but to simply state that the cortex supports memory and parallel computation. The recall is stochastic, unlike conventional databases, and it's about what memories have been found useful in past experience. Perception involves putting the sort of the details or models of the world around you into the cortex for accessed by the other systems. And the system 1 is sort of intuitive, emotional thought, and I mean, it's very rapid, but it's opaque. System 2 is slower, sequential, deliberative thought, which is open to introspection and can happens at many different levels of abstraction. And actions are things like playing the piano, where if you think about all your finger placements, you couldn't do it. You have to learn to be able to think, let's see the notes, and then make your fingers do the work without you really thinking about it. Sort of delegating, you're delegating control to the cerebellum and the circuit it connects to with the cortex. So it allows real-time control of many muscles without blocking cognition. So I quite like Keith Stanovich's tripartite model of mind. So it uses a slightly different terminology, type 1 and type 2, rather than system 1 and 2. This is focusing on the processing. So type 1 is fast and automatic, like recognizing a cat in a photograph or a traffic sign when driving a car. And that's sort of autonomous mind. And then we have type 2 processing, slow, deliberative, and open to introspection, such as mental arithmetic, and formed by chaining type 1 processes using working memory. And so we have the kind of algorithmic mind, kind of the rule-based stuff, but we also have the reflective thinking about thinking. Like how am I doing at this task? Is there a better way of doing this task? How am I keeping up with the values I have? So I mentioned the work by Anderson at CMU on ACTA, And so within the cognitive AI community group, I came up with developed a simple, lightweight syntax for what are called chunks and rules. So a chunk is essentially a collection of named value pairs, and those values can reference other chunks to form a knowledge graph. And they can also be used to express rules, sort of if-then production rules. And so, for example, I've applied this to smart homes and sort of robots within a factory and things like that. So there's some web-based demos you can look at. But essentially, we have chunks and rules, and the chunk has a type and an ID and a collection of properties. The properties are named values. The values can be names, numbers, and variables. And then the rules are essentially a sequence of conditions and a sequence of actions. And the conditions are conjunction of conditions. And then the actions either update the buffers in the model, or they invoke operations within the cortex or these external systems, for example, to drive the control of a robot arm. And the idea here is the rule engine is connected to the cortex via buffers, which hold a single chunk. And that means that the rule engine can scale better than if you have direct access to the databases. So that the chunks sort of represent in some ways the bundle of nerves to particular parts of the cortex. And yeah, so the reasoning can be decoupled from the real-time controls. And there's a predefined suite of built-in cortical operations where the name's sort of inspired by the HTTP methods. So what are the limitations of symbolic AI? So it's generally handcrafted, keep track of the time. But it's really, they're impoverished representations compared to the subtle context sensitivity and precision common in the real world. You have to sort of distill away from the real world and all its complexity to make the symbolic models. And that means that in practical use, there are often problems you run up against kind of the limitations of what you've chosen. And it's expensive to develop and maintain, and as a result, very hard to scale up knowledge-based systems using symbolic AI. There are recent successes for generative AI, so that computers can be very much better at knowledge engineering than we are. So a rhetorical question is, are we wasting our time on symbolic AI? So now for the limitations of generative AI, on the other side of the hand. So its astonishing ability to learn billions of parameters in complex neural networks about backpropagation, amazing abilities in dealing with text and images, and now speech, music, video, and 3D. So video, the Sora was recently generating 1 minute long, very compelling video. And there are many opportunities, therefore, for multimodal applications. And I think that as they sort of start doing more work on training against video, that will also allow the systems to learn emotional models, which will be important for sort of interaction. And then we have this idea of chain of thought plus reinforcement learning of human feedback. This is sort of surprising ability to pass even some of our human exams using the fine tuning and other techniques for ensuring safe responses, including like bootstrapping as self-critique from a set of principles. Then there's prompt engineering is a valuable new skill, but the language models will soon be able to craft good prompts for us. It's already the case. For example, if you want to use DALL-E from Bing, that is a good idea to ask Bing to generate the prompt for you. The generative AI is prone to bias, distractions, and hallucinations. It's weak on logical reasoning and semantic consistency, and I'll show you some examples. So in the top picture on the right, with stable diffusion, it looks convincing at first part until you look at the hand and you see, it hasn't really got a clue how many fingers people have. And then below, I gave a prompt to DALL-E, 3 red balls and 2 blue cubes on a wooden floor. Didn't do really well, did it? So it's got distracted there. And again, if you ask, you ask a ChatGPT, is 1 kilogram heavier than 2 kilograms? It correctly replies no. But if you then say, is 1 kilogram of lead heavier than 2 grams of feathers, it gets it wrong because it gets distracted by the descriptions, the adjectives. So there's also a lack of continual learning and temporal memory. They're very expensive to train foundation models, which makes it very difficult for independent researchers. And it's very different from the way the human brain works. So this is not my insight, but others. It's more alchemy than science, but it's still early days. So language models are kind of feed forward. They take the prompt, they encode it, and they feed it through a set of layers, and then decode it to get the likely response. And the neural network is used for statistical prediction of response for the given prompt. And the text you encode it as sequence tokens as vectors in embedding space, including the kind of position of the words in the text. And then you use multiple layers of transformers, which provide for long-range self-attention and hierarchical dependencies. And the parameters, the billions of parameters are trained for backpropagation using a loss function based on text prediction. There's no short-term memory and no continual learning. What am I doing? Latent semantics are kind of buried deep within the network, in an opaque way. So the network connections encode the knowledge in a distributed fashion using vectors rather than symbols. So you can't really see what's going on easily, and it's very hard to generate explanations of what its choices have been. So it's reliant on attention as a surrogate for reverse flow of information, because remember, this is feed forward only. So, if the choice, the meaning, of the sense of a word and the meaning of a word depends on the kind of words around it. So that's kind of what I mean there. And then obviously the semantics, and as I said, in the nearby words and words that act like verbs, slot fillers, and so on. So how do you connect things up, attach prepositional phrases, and so forth? And the outer layers, the top and bottom layers, are more closely related to word tokens, and the middle layers are related to semantics and pragmatics, because we've got an encoding into semantics, then back out into the response. Then we can tailor the context. We can provide a kind of inject a prompt before the user's prompt to sort of guide what kind of response we want for the particular application. So it's letting the language model know what we're hoping for in the response. There's feedback as a sort of surrogate for short-term dialogue memory. So as the response is generated token by token, it's fed back appended to the end of the prompt to generate, to provide a sort of short-term memory, making it possible to generate lengthy responses, or they tend to drift off after a while. Then there's prompt engineering. Good prompts give good responses. Different kinds of prompts, and generally speaking, you need to specify what you want. For example, saying each title should be between 2 and 5 words long. It provides some examples, and you can see from one of the classic key papers on this on the right. And using worked examples, improving but also using reinforcement learning feedback to make it work better for a particular domain. So it's sort of the post-training of the pre-training. But it's open to adversarial attacks. You can craft prompts which bypass the sort of safety measures, and Google and others have run afoul of this already. You can ask the LLMs to craft expert prompts for you, and so there's the example here of using Bing search to generate prompts for DALL-E, and produces better results than the prompts you might initially think of. And this chain of thought prompting is sort of saying, try and work on things step by step. And you can say that, please, explain step by step. But it's better still if you can provide some examples of what the steps are, and then the system is less likely to get distracted and make mistakes. Then we have retrieval augmented generation, that the language models are trained once, and their knowledge is static. Once it's been trained, it's kind of like frozen in time. And they also have difficulty in generating citations to the knowledge which is embedded in their parameters. And the workaround is to query an external knowledge graph to obtain a list of relevant sources and citations, and inject this back into the context. And then when your prompt, instruct the language model to generate links to those citations. So this allows for up-to-date information and avoids the needs for the language model to include sensitive data like personal data or corporate data you don't want to leak out. And so this process, because it's like a query, you want to do it based on the user's prompt. So we can use vector-based indexes, which can take the user's prompt and then find the most likely, most relevant citations, and then process those to generate the prompt to insert before yours. So what are we looking for in the artificial general intelligence? So the creativity in problem solving, with the ability to generate and adapt plans as needed, a good grasp of common sense knowledge and skills, cause and effect, feasible reasoning, understanding human feelings and values, which are of course important to augmentation, continual learning with models of the past, present, and future, which we can't do with generative AI at the moment, replacing prompt engineering by allowing the system to learn from the kind of responses most people prefer, reflective cognition and utilizing models, the agent skills and performance in carrying them out. And likewise, there's others, like the humans, which involves the theory of mind, the ability to explain itself so that we can easily appreciate, which may vary from one person to the next. So, for example, the explanations you generate for a child would be very different from those for an adult. And also we want these systems to adhere to the values we demand of them. So we don't want them to give racist, sexist, or inflammatory responses, for example, instructions for making bombs. We want the agents to be unambiguously artificial agents and not to be confused with humans. That means that they need to be labeled as such. The applications like the smarter robots, self-driving cars, and so on, the resilience to the unexpected, unlike sort of handcrafted knowledge, which is very brittle. Tools for boosting human creativity and effectiveness, better productivity for a more prosperous society, but only if we share the benefits. As trusted personal agents and help us deal with a complicated world and look after our privacy, finances, and health. And then for health, cybersecurity, for stronger cybersecurity and for countering disinformation, harmful content, and conspiracy theories and social media. So I think this is where the social media companies need a lot of pressure to make them invest in this, to make their systems much safer, reduce the harmful effects, for example, on children. And I believe that AGI could one day win arguments of politicians and lawyers, leading to stronger democracies and better laws, because they will be able to do so by in-depth access to knowledge, including which arguments best convince people emotionally and intellectually. They'll just be able to do much better than the average human, or even the exceptional human. So using these rhetorical approaches, like I described before. So now, towards the last part of the talk, I'm going to talk about kind of the ideas for future neural networks and the work that I'm doing. So the biggest considerations are how to support the memory of time, the episodic memory of past episodes, and continual learning. So you want to enable a mix of type 1 and type 2 processing along with cognitive operating system. Like how do you balance the time allocated to different competing tasks, akin to a mental operating system with feelings and drives. So this is where it makes sense to start introducing something analogous to human emotions and feelings. Then there's reflective cognition along with episodic memory to support situational awareness, including self-awareness, self-assessment, respective execution of high-level goals. I think it's easier to discuss sentience in that sense than it is to discuss consciousness in general, which is harder to define, including the sort of so-called philosopher's problem of consciousness in respect to subjective experience and qualia. And if all experience reduces to information processing of systems and neurons, then qualia is a non-issue for artificial agents. We need to support continual learning guided by effective cognition. As humans, as we're learning something, it's not all automatic. We have to think about it. We have to think about, do we have a misunderstanding? How can we fix that? And what would be an interesting thing to look at? So how does the brain make memories? And so we have like episodic memory, associative memory can be used as a record akin to a personal diary, along with holding temporal relations that allow past experiences to be called in sequence. Then we have encyclopedic memory, such as time-dependent facts, such as birds fly and dogs bark. And we have this idea that episodic memory is key to supporting abductive reasoning, what-if reasoning, creating and updating plans, reasoning about cause and effect, and thinking about other agents' intents and state of mind. Is that animal about to eat me kind of thing. So retrieval of memories uses a combination of what, where, and when cues, and then they're consolidated in the neocortex after initial modeling in the hippocampus. Anyway, there's an interesting paper there. Then, how can we lower the hurdles for researchers? So language models with billions of parameters are very expensive to train. It's prohibitive for many researchers in universities and in independent institutions. This is the barrier for work in innovative new network architectures. If we want to avoid just leaving research to the very large organizations, we need to find ways of lowering the hurdles. So a solution is to use smaller data sets and fewer parameters, and chosen to support your research aims, like continual learning, episodic memory, and reflective cognition. And this is one way of approaching this is to use machine-generated data sets. So, for example, Microsoft's is a very interesting paper, and they produced some stuff on, I think it's on Hugging Face, maybe. Basically, they generated out a smaller data set, which has been generated from a language model, which you can then use to train smaller models more effectively. Then you can use knowledge graphs and stochastic rules, which trace across a knowledge graph to generate training examples. And of course, handcrafted examples are still very valuable, particularly in the post-training. And then there's different ways to learn. At the moment, neural networks, large language models are only really learning from observation. But there's humans, we learn from instruction, like in classes, at school. university. And you also learn for experience, where you try things out. You experiment and see whether that pile of bricks will be stable or will fall over as a toddler. And the idea here is to evaluate different designs and then select the best for the scaling up, because that's the expensive bit. And that the small AI models, there's an interesting use of them at the execution at the edge with a reduced processing power rather than everything being in the cloud. So continual learning, how are we doing? Yeah. Generative AI suffers from catastrophic task interference. So if you try and teach it a new task, it dramatically degrades the competence on the previously learned tasks. And there are limited workarounds for transfer learning, which is referred to as fine-tuning. And there's some potential solutions and a bunch of technical things like weight regularization, sparse networks, lateral inhibition, self-assembling neural networks, and which can be combined with genetic algorithms. So, because in the brain, our synapses are constantly changing over our lifetimes. And then we have the idea of different parts of the cortex serve different roles. Like one part of your cortex specializes in face recognition. And so, again, can we match the tasks to different neural modules? Then we have meta-learning, which is learning to learn, which is where the reflection comes in. And then giving agents dynamic access to models of the past, present, and future, the episodic memory. Memory for different timescales. So we have the long-term, short-term, and working memory. So the long-term in the human brain is for the neocortex, the short-term with the hippocampus, and the working memory is kind of activations. What's the brain firing up right now? Then we have perception-related memory. So there's the classic paper by Baddeley and Hitch back in the 70s. And so the phonological loop, how much, if you hear somebody say something, how much can you remember for how long? And then the similar thing for your vision, the visual sketchpad, which is even shorter. If you try and remember some picture, then you try and test it, you realize you don't remember so much at all. Then there's situational awareness. You need for a detailed short-term memory to make decisions, urgent decisions. But learning involves, you want to avoid undue emphasis on the most recent events versus the older events. You need to be fair across the samples, as it were. And this is analogous to the difference in the hippocampus and the neocortex. And so, there's some related topics for exploration. So human learns from a few examples, but existing language models learn from vast corpora. The so-called single-shot learning for language models is based on the prompts and doesn't update the model. So how can we mimic the roles of the hippocampus and the neocortex? And so one idea is to have separate models for short and long-term memories and then blend them in a manner akin to transfer learning. So that's something to explore. Then there's the idea of the input and outputs of the language models or tensors. So, the actual out parts are this batch size, sequence length, and vocabulary size. And, within the model, that's compressed down into a smaller vector. This assumes a fixed vocabulary size of tokens as words, characters, or some intermediary thereof. An alternative would be to use a vector database that maps encoded tokens to words or character sequences. And you really would like to have something you can learn vocabulary incrementally, just like a human. And so, yeah. So then there's this idea of combining feed forward with feed backward connections, because in the brain, feed back pathways are much more numerous than feed forward pathways. And the brain, that's telling us something when we have yet to sort of really explore that. So there's the latent semantics in the form of activation levels of artificial neurons, which can be seen as working memory, providing the context to for selecting word senses, prepositional attachments, and so forth. And the current models use sequence lengths with many thousands of text tokens. For example, GPT-4, I believe it's something like 8,000 tokens. And the tokens are, roughly speaking, in their sense, roughly equivalent to a word. Sometimes less. Long-range attention is very expensive because you want to compare all the pairs of tokens in the sequence, and that scales quadratically. And feedback is progressively by appending the generated tokens. So instead of limiting the encoder-decoder sequence length, why not use feed backward connections from the latent semantics to lower layers to mimic human language processing? What kind of feedback? You can have retained state, where you have, if you stepwise processing, then you can hold the state. And there's already examples of this, for example, in the long short-term memory networks. And this is the key to sequential cognition. But you also have continuous feedback, as in dynamic feedback, which I think is key to some lower level parts of language processing. So there are plenty of design choices for researchers to look at. And is feedback implemented multi-layer connections or a sequence of layer-by-layer transformations? Does it skip layers or not? Are transformers integral to feedback, or should we can use other architectural building blocks? How do we ensure that dynamic or continuous feedback is efficient and so like strong attractors for quick stabilization, akin to the collapse of quantum superposition of states? So that's something where, can we draw on insights from quantum mechanics, and what are the implications for deep learning? And then there's the idea, rather than having one architecture for, homogeneous architecture, as in the current models, can we introduce heterogeneous neural network architectures featuring modules with different kinds of architectures within them for different purposes? Then we have human-inspired language models. The human language processing, as I said, is sequential, hierarchical, and predictive. We have these sort of buffering constraints. So you can implement that as a small sliding window of a text tokens of long-range attention replaced by attention to the latent semantics. And I think that really lends itself to the idea of a model, explicit model of producers and consumers to reduce the cost of self-attention. If we can have the network sort of eventually manage or track producers and consumers with, for example, I have a prepositional phrase as a producer of meaning, and then a consumer will be a verb, and you're trying to attach the prepositional phrase to a slot on the verb. Then so that will reduce the number of things you have to consider and reduce the cost considerably. Then we have the idea for modules which understand words and their morphology and learn to associate words with the lexical features, and can be invoked asynchronously to generate the characters. Current language models, you have to, if you have a character-based encoding or a tokenizer, then you have to run the entire model once for each character. This is very expensive. If the model could figure out what word it wants to generate and pass a vector for that across, then the system responsible for words could go away asynchronously in the background to generate the characters, while the rest of the system carries on to look at the next word. So we can have to retain semantics from the previous processing step and combine that with input from the lower layer. This needs to be informed by mathematical models, not knowledge representations. And so there's some techniques involved, for example, using turplets matrices for circular convolution, and techniques which take advantage of the Zipf's law, which is essentially computation on the most common words. For example, in the Penn Tree Bank, 87% of documents are covered by just 20% of the vocabulary. So, if you make sure you can deal with the common words cheaply, then you could put more effort into the rare words which occur, like 1 in 10 or 1 in something like that. And maybe the idea is to reduce the cost of pre-training. And there's a similar work. There's papers like Linformer as an example. There's several of these things with self-attention and linear complexity. Then there's, what additional neural models we can think of. There's sequential cognition, which is like the chunks and rules. We'd like a chunk rule engine, which is a feed-forward network, which takes as input the kind of latent semantics from the middle of between the encoder decoder for the language model, and updates those models. And if you think about these things, image generators, for example, with the blocks, like how many blocks are, I want to have 3 red blocks and 2 blue cubes, or whatever it might be. And then we can have rules which can operate over that and count how many there are and make sure the model is correct. So we can then corresponds to production rules for conditions and actions. And this network can be trained from examples of reasoning and stepwise tasks using deep reinforcement learning. And so working memory corresponds to the deepest layer, or the middle layer, as it were, of the language model. So with the values retained from the previous processing step, and then the output from this module updates those values. So that way the things can carry on thinking without any prompts, right? Current systems, they're only driven by the prompts, but with this system, it can carry on thinking. Then we have different kinds of memory, like episodic and encyclopedic memory, acting as short and long-term memory, with CRUD operations, create, read, update, and delete on a vector database, and additional operations as needed, mimicking the human forgetting curve. So that's stochastic recall based on what proved most useful in past experience. And then there's the idea of episodic memory. The way you might implement it is by recording salient details from a snapshot of working memory. So using sort of similarity notions like the cosine metric. And then we have the idea of supplementing this by relationships between episodes and the process of memory consolidation. And for example, this was first referred to in the writings of Quintilian, renowned Roman teacher of rhetoric. He noticed the curious fact that an interval of a single night will greatly increase the strength of memory, representing the possibility that the power of recollection undergoes a process of ripening and maturing, during which the time on which intervenes. So semantic interoperability, which is knowing that we understand each other. Oh yeah, yes, it's an example of the generative AI lacking semantic consistency because the body is somehow not attached to the legs. So ensuring mutual understanding, people keep written records when they don't want to rely on fallible memory. The same applies to businesses. So everyday language isn't good enough when you want to be sure of a mutual understanding. For example, business contracts are written using standardized terms and legal language. And for technical exchanges, we likewise use structured data with agreed data models and semantics. This relies on symbolic representations, and we will continue to need this as we make greater use of AI. And so this forms knowledge graphs as evolution of databases and the importance of standardized vocabularies for shared understanding. And so I think at the moment, these ontologies, like our ontology, is so handcrafted. But I think handcrafting knowledge graphs along with the rule sets is difficult and time consuming. This makes it hard to scale up. Self-guided machine learning of neural networks is very much easier to scale up, but suffers from lack of transparency. So how can we use AI for collaborative knowledge engineering, like the human partner working with an artificial agent, as shown in the picture in the right? The agent operates in knowledge graphs and rule sets guided by the human partner. So the humans are sort of curating at a distance, as it were, and the AI is doing kind of the hard work. And it's also able to update rules as the ontologies are revised, and supporting versioning for old and new applications. So if you've got applications you want to continue working, then you need to be able to have some of the knowledge representations. If you change them too dramatically, your application will break. So there's the kind of reasoning involved to allow applications to continue to work as you update the ontologies to support the new requirements that you discovered. And again, here you can see that DALL-E has got this unsupported tablet floating in the air. So it's obviously hasn't quite figured out the physics, that things need to be supported. So I'm very close to the end. The architecture of a new symbolic cognitive agents, this is very much sort of like iconic. The idea that we can have text input, sensors, and services being encoded into the network, and then the decoding is text output, also could be multimodal, like images and so forth, diagrams, tables, math. We have controlling of actuators, and also services like talking to external databases, which then feed back into the input. And these actions can be delegated to external real-time control loops and so forth. So this is iconic, not intended as an accurate representation, but it gives a general idea. If the feed forward is type 1 processing and feedback is sort of type 2 processing. So summary and conclusions, expanding from logic to argumentation, that looking for help with use cases and examples of good practices of argumentation. So if you ask in the system for help, it can provide you a well-crafted argument. Machine learning beats handcrafted knowledge, and that's abundantly clear now. There's an ongoing role for symbolic AI for semantic interoperability. There's plenty of opportunities for work on human-like AGI without the need for huge budgets. And there's help needed with use cases and training materials for that, and also the mathematical foundations, and of course, the compute resources for training large models. So please get in touch if you can help. And then finally, I've got sort of some discussion topics. So what will human-like AI do for us? What's the difference between generative AI and human-like AI? Is there a role for smaller AI models? What is the relationship between neural and symbolic-based approaches? And does the semantic web need RDF? So I guess I won't read out the text below. I'll come back to that in just a sec. But so now is the time for questions and comments. So open the floor. Thank you.
There've been a couple in the chat here. I'm going to start with Daniel's. Do you have an instinct regarding what kinds of semantic data products enterprises can be making for themselves now that will be useful across a variety of AI applications? Examples, ontologies, fine-tuning sets, knowledge graphs describing domain expertise, documentation, etc.
Yeah, I'm not an expert into that, but I think that one of the things is that we get knowledge, information comes in many different formats. So some of the work going at W3C on being able to express rules for translating between different formats to RDF, like the RML work on RML, is kind of relevant to that. I think that trying to capture the agreed knowledge within knowledge graphs across the corporate processes is sort of valuable. And then trying to gather the kind of the training materials that we can use either with today's AI or with tomorrow's. Trying to gather what kind of performance, what kind of tasks you'd like it to help you with. So it's trying to figure out how you can collect those training data sets.
Good. This one goes back earlier with the discussion on PKN. What kind of reasoner would be used for data expressed in PKN?
At the moment, I have a proof of concept reasoner. So it's works from the it starts by from the supposition in question, like the query, and then works back to the facts, as it were, in the knowledge graph. And so for that, it's using a bunch of sort of heuristics, like reasoning across relations, reasoning across implications. And we want to be able to extend this further, then obviously to include reasoning by analogy and the fuzzy reasoning. So we already have some of that in there. And then more generally, there's this idea of reasoning at different levels of abstraction. So the rhetorical stance of Aristotle's guidelines, where you want to be able to figure out, how do you establish credibility for your argument? Where's the data coming from? Do you trust it? Who do you trust? Why you trust it? Then the kind of the rationality, the rational arguments, but also the kind of potentially kind of emotional aspects to arguments. We can move beyond where we are now today. Obviously, in marketing, when you want to reach out to a customer, those kind of emotional drivers are really important. So this is something which I think will become in scope. And yeah, and then also kind of what rhetorical questions might be relevant. So this involves kind of a level of how to express strategies and tactics for that kind of reasoning. I think that the work into feasible reasoning is still at a very early stage, though.
Dave McComb.
Wow, Dave, that was an amazing amount of stuff to digest in that amount of time. But I want to drill down a little bit more on the PKN. Is that purely additive to a knowledge graph? In other words, are those little things that you called out, are those actual predicates that we would add to a knowledge graph? And is the query language sort of additive to something like Sparkle? Could you mix and match it? Could we, or is it a completely separate thing where we start over?
Hang on just an example. Thank you, Word. I mean, PowerPoint. I'll get there in a minute. Right. So these are some examples of statements. And so some of these statements, correspond, like climate of Belgium includes temperate, kind of corresponds to, in some ways, to an RDF triple, right? So that's kind of low level, but it also can include the, it's like includes. So there's this operator which specifies this, the kind of a set kind of characteristics. Is it temperate, in which case it excludes other values, or are you talking about a set which you combine? So if you have several different statements, can you combine the information from these different facts in your argument, or are they orthogonal, mutually, separable? And then there's the kind of the context, like the four plumbing or four circuits, like a duck is similar to a goose in respect to the length of its neck, but not in respect to the sound of its call. Then we have things like the qualitative metadata associated with these statements. So this is going beyond. So essentially, the RDF involves a very simple symbolic sort of directed, label-directed edges in a graph. This is at a higher level than RDF and includes additional richer information.
So wait, let me process that. So if we wanted to add PKN to a knowledge graph, is it an ontology are these blue things properties? I realize they're special, but do we express knowledge using these predicates and then put another reasoner over top of that, or is it something over on the side?
No. If you want to be able to reason, make plausible inferences, then you need a defeasible reasoner, which understands the qualitative metadata and how to combine different statements, different inferences. So it requires a new reasoner.
Right, but if we want to combine our existing information with
right, well yes,
some of this,
right, the existing information, that's largely speaking facts.
Yeah.
And the question of, are those facts absolute? Do they have any metadata associated with those facts? Like, for example, we can talk about provenance. Where do these facts come from?
Mm-hmm.
How much are they trusted?
Right.
So these are things which RDF is kind of like very low level. And normally in RDF, you have to express these using a combination of triples. And some of this stuff can be operated on with a kind of a reasoner based on description logics, but other stuff goes beyond that, and then you really have to roll your own reasoner in your own application code. And that's the current situation today, and that's basically limits the flexibility of your applications and increases the cost for evolving them to support new needs.
Peter.
So I was thinking, Dave, that you may need something like the Kinefin framework to kind of work out what, Dave Snowden's ideas about the different types of problems that we have, clear ones where we understand exactly where it is, or complicated ones where we implement good practice and avoid the sort of wicked problems, which are just going to be computationally intensive and going to take us down into a rabbit hole that will be difficult to get out of. And I was just wondering, what would be the sort of heuristics that would help us know which one of those we're into?
Right. So if you're talking about description logics and like the different levels of OWL, then as you increase this expressivity, the reasoning time can explode. So whereas in a kind of a plausible reasoning environment, then we have qualitative metadata, and that allows us to sort of manage where the reasoning takes us. There's no point in reasoning if the likelihood is so low of the certainty of some statements, you're wasting your time. So you can just prune the search at that point. And so the idea is to use the qualitative metadata to control the search in some ways at a low level, but the high level you need these strategies and tactics to guide the search in the direction which is useful.
And how mature are those from what work that you've been doing within these sort of examples? Do you have any examples where you've got indicators that tell you to sort of stop digging, basically?
Well, in the actual web demonstrator, it sort of looks back for the, it stops, vanilla, it stops after it's found the first sort of facts support the case, right? But if you click the checkbox, work harder, then it carries on further. And so that's part of that demonstrator. But it's only a crude initial demonstrator. I think there's plenty of work to be done. And there's the body of the argumentation theory is a strong field of research in its own right. But at the moment, they haven't really, the people who are practitioners haven't really taken the qualitative metadata into account. So I think this is where I thought that Collins's insights were particularly important. And also I think that with the advances of machine learning, as we've seen with generative AI, that a lot of the qualitative metadata, we should leave that to machines to discover. We shouldn't be handcrafting this stuff. We should be guiding how machines harvest this stuff, curating the data sets, but handcrafting all this is just a waste of time in the long run. In the short term, sure, but in the long run, I think that that's the way I see it. And of course, related to that, the idea of being able to generate knowledge graphs from, the distill knowledge down into knowledge graphs, symbolic knowledge graphs, is another field of research.
Good. We're right at time. I'm going to email the recording today, and Dave, I'm going to include your email in your slides once again, so everybody can connect with you offline. Or I know you mentioned, you know, some assistance with research and things would be valuable. So I will include all that in the email that I send, and keep the conversation going that way.
Thanks so much indeed, and thanks for arranging this opportunity.
Yep, absolutely. Well, thanks everybody. We look forward to seeing you next month.
Yep.
Bye.
Thank you. This has been fascinating. Thanks very much.